Brandon, did you hear what the weatherman said on the Channel 4 news?
No. What did he say?
Here, watch.
It's really windy out here, folks, so you better check your spare tire if you plan on traveling in the near future.
Oh, we're good. I already checked the spare tire this morning.
Wait, why did you check the spare tire this morning?
Because it's National Check Your Spare Tire Day?
Oh, really? I didn't know that.
Yeah. But you know what would be fun? Is if we figured out the rate at which the volume of the tire changes as we pump air into it. But I don't know how you do that.
It's simple. Calculus. Alright, so the shape of a tire is roughly that of a cylinder. So let's draw this out here. So according to our measurements, we know that the radius of the whole tire is 12 inches. So let's call that big R. Now we know that the radius of the part in the middle, the cylinder that we're going to take out, is 9 inches. So let's call that little r. And then we know also that the height is 6 inches. Let's call that h. So this is when the tire is fully inflated. So from here we can see that there's a proportion between big R, little r, and h. So we know that little r is 3/4 of big R. We also know that h is 1/2 of big R, or 2h equals r. So we want to find out what's happening when the height is equal to 4 inches. What is the rate of change of the volume with respect to time? So we know that when pumping with an air pump, we can pump in about, let's see, dH dt. We know we can inflate the tire at about 0.08 inches per second. Alright, so now we got to write an equation for the volume. So for the equation of the tire as a whole, we have V equals pi big R squared h. Now we have to take out the cylinder in the middle. So minus pi little r squared h. So using our proportion up here, we know that V equals pi big R squared h minus pi 3/4 r big R squared h. Now we take the square root and we apply it to the terms on the inside. So we have the volume equals pi big R squared h minus pi times 9/16 big R squared h. So now we have 1 pi r squared h here and 9/16 pi r squared h here. So we can subtract those. So when we do 1 minus 9/16, we get that the volume equals 7/16 pi big R squared h. Now what we're going to do is we're going to get this in terms of h, since we know the rate of change of h. So V equals 7/16 pi. If we have here, we have 2h equals r squared, so we can put that in here, 2h squared times another h. So we take the square root, we have V equals 7/16 pi 4, then we have h squared times another h would be h cubed. So the 4 cancels out with the 16, we have 4. So V equals 7/4 h cubed pi. Now what we can do, go up here, is we can take the derivative. So I'll write this again. V equals 7/4 h cubed pi. So when we take the derivative, we have to take this 3 and multiply it by the 7/4. So we have dv over dt equals 21 over 4 h squared pi, because we subtract 1 due to the power rule, but then we also have to multiply by dh dt, because we're taking it with the derivative of the volume. So now we can plug in when h is equal to 4. So we have derivative of v with respect to t equals 21 fourths 4 squared pi. And then we know that the rate of change of h with respect to t is at a constant rate of 0.08 inches per second. So we can multiply by 0.08. So when we get this, we have dv over dt equals 21 over 4 times 16 pi times our 0.08. So 16 will cancel out with the 4 and we'll have 4 left. 4 times 21 is 84. dv over dt equals 84 pi times that 0.08. So if we have 84 times 0.08, use the handy dandy calculator, we get dv over dt equals 6.72 pi. So dv over dt, if we take that 6.72, multiply it by pi, we get 21.112 to 3 figures, and our units are going to be inches cubed per second.